When we talk about artificial intelligence, one of the biggest, most basic challenges is just, well, getting from point A to point B. Now that sounds super simple, right? But it's actually the secret sauce behind your GPS, the robots that build cars in a factory, and yeah, even the enemies in your favorite video games. So how does an AI find the smartest path and not just stumble into any old path? Let's dive in. You've totally been there, right? You're in a video game, you're hiding, you think you're perfectly safe, and then somehow an enemy just navigates this incredibly complex map and makes a perfect beeline right for you. They're not just wandering around hoping to get lucky. Nope, they're using a really powerful AI technique called informed search. And once you get how it works, you start to see how machines can think their way through all sorts of problems. Okay, so here's the real challenge. For a computer, trying to find the best path, whether it's in a game or through a city's road network, is like being dropped into a maze the size of a planet. I mean, it could try to check every single possible route. We call that a brute force approach. But the number of paths just explodes. It becomes astronomically huge. So for any problem that's even a little bit complex, that's just not going to happen. It's impossible. So if checking every single path is totally out of the question, how on earth does an AI do it? Well, it uses a clever trick. You can think of it like a kind of digital intuition. And that brings us to the real hero of our story today, the heuristic. This little thing is the magic ingredient that turns a blind, hopeless search into a smart, guided exploration. So what is a heuristic? At its core, it's just an educated guess. That's the best way to think about it. The algorithm doesn't know the exact perfect path, of course, but it has a really good hunch about which direction looks the most promising. It's a simple rule of thumb that helps the algorithm guess how close it is to the finish line, and that lets it make much, much smarter choices without needing to have all the answers up front. And this picture illustrates the whole idea perfectly. That winding road labeled G of n, well, that represents the actual cost of the path we've already taken. That's the ground truth. But that dotted line, H of n, that's our heuristic, that's our hunch. When we're talking about navigation, this is often just the straight line distance to the goal, as the crow flies. It's not the real road distance, obviously, but it's a fantastic estimate that helps the AI decide which turn to take next. Now, here's where it gets really interesting. Different algorithms use this hunch in totally different ways. It's definitely not a one-size-fits-all kind of thing. And this creates a really fascinating trade-off. Do you want pure, raw speed, or do you absolutely need to find the single most perfect path? Let's take a look at how two really famous algorithms handle this exact problem. First up, we've got greedy best first search. The best way to think about this one is as the impatient sprinter. Its evaluation function is super simple. F of n equals H of n. What this means is that it only cares about one thing, the hunch. It totally ignores how far it's already traveled and just barrels towards whatever looks closest to the goal right at this very moment. So what's the result of that approach? Well, the greedy algorithm is unbelievably fast, but that impatience is also its biggest weakness. In AI terms, we say it's not optimal, which means it often finds a path that's way longer than the best one. And it's also not complete. It can get tricked, run into dead ends, or even get stuck running in an infinite loop. So yeah, fast, but definitely reckless. Okay, so if greedy search is our impatient sprinter, it's time to meet A-star search, the wise strategist. A-star takes a much more balanced, much more thoughtful approach. Its evaluation function is F of n equals G of n plus H of n. You see what it's doing? It's combining the cost of the path it's already traveled, G of n, with the estimated cost to get to the goal, H of n. And this balance is exactly why A-star is so incredibly powerful. This isn't just some niche algorithm you learn about in a textbook. As the source material says, A-star is the most widely used search algorithm in AI. It really, truly is the gold standard for this kind of pathfinding. Let's just break that down real quick. First, A-star looks at reality, the actual cost to get to where it is right now. Second, it adds in its educated guess, that heuristic for the rest of the trip. And finally, it chooses to explore the path that has the lowest combined total. It's this beautiful blend of respecting the past while intelligently planning for the future that makes it so efficient and so accurate. But even the wise strategist has an Achilles heel. Of course it does. A-star's perfection comes at a cost, and it's a cost that becomes a major, major problem when we're dealing with truly massive mazes, like, say, mapping the entire internet or planning logistics for a global company. And here it is. This is the main drawback of A-star. To guarantee it finds the best path, it has to keep every single option it has ever considered, every one of those little nodes, in its memory. For a small problem, that's totally fine, but for huge real-world applications, this becomes a critical failure point. I mean, imagine a GPS trying to map every possible route variation in an entire country in real time. The number of nodes becomes billions, and the system just plain runs out of RAM. So to solve this, researchers came up with some really clever memory-efficient versions. Take an algorithm like recursive best first search, or RBFS. It can still find the optimal path, but it does it while using very, very little memory. The trade-off? Well, it sometimes has to forget a promising path and backtrack to explore another one, which can take more time. Others, like SMA star, are designed to just intelligently make the most of whatever RAM you happen to have available. Okay, so we've been deep in the theory, we've talked about the algorithms, their pros, their cons, but this isn't just some abstract computer science puzzle. These concepts are the invisible engines powering technology that you and I use every single day. Let's look at where these guided explorations actually show up in our world. Right, we started with video game enemies, and that is a perfect example. But this is also exactly how your GPS finds the fastest route, dodging traffic in real time. It's how telecommunication networks route your emails and data packets all the way around the globe in milliseconds. And it's how huge companies plan their shipping and supply chains to be as mind-bogglingly efficient as possible. In the end, it all comes back to that one single powerful idea. And the source material puts it so elegantly. These algorithms use heuristics to turn the blind search into a guided exploration. They give AI the power to solve problems that would be literally impossible to crack just by using brute force alone. And that leaves us with a really fascinating final thought to chew on. The effectiveness of all these algorithms, every single one, depends on the quality of their hunch, of their heuristic. So the real question is, as AI gets better and better at creating more sophisticated and more accurate heuristics, what currently unsolvable problems, from discovering new drugs to modeling our climate, could they finally crack?